Okay. Yeah. So, hi everyone. Welcome to the IRCS verification seminar series. We are happy to have Subhajit here with us. Subhajit is an associate professor at in the CSE department at IIT Kanpur, and of course, he's worked on a lot of very interesting problems in many areas of testing, verification, analysis, optimization. I think he also uses a lot of formal method techniques, and along with that, I think he's lately been using some data-driven techniques, and I believe he'll cover both these aspects in his talk today. Yeah. So Subhajit, over to you.
Thank you, Madhukar, for the very kind introduction. Right. So, like as Madhukar said, so this talk is about using a combination of testing and proof techniques to solve a problem which is quite relevant in this community. So we will be we have been last 4 to 5 years we have been focusing on this problem of analyzing what we call incomplete programs, or what we call programs with closed box components. So the idea is that let us say I have this program, but this program has a function foo, which say accepts two numbers or two parameters a and b, and returns an x, a value x. But the problem is that you do not have access to the source code of foo, which makes any sort of reasoning on this program very hard. Now, this foo could be, for example, a cloud API. So, like, of course, we're sending messages and the computation is happening in the cloud, and you're simply getting the response back. So there is no way to even understand what's really happening there. It could be a library function. It could be an external library, perhaps a proprietary library. So for which the code is not available again. And again, you may not know what's really happening within the library. Or it could be something where you do have access to what you would call the source code, but then it's just too difficult to analyze. For example, it could be a very large machine learning model. So any sort of formal reasoning on such models tends to be very hard. So the question is that, is there a way of sort of combining verification techniques with certain other techniques, say certain fuzzing techniques or certain other testing techniques, to enable verification or some sort of confidence in these programs. So now there could be multiple ways these components sort of manifest. One could be that these components could be completely unknown. You may not even have access to even executing them. Or it could be that you do not have access to the source code, but you do have access to their some sort of implementation, which allows them to call these methods. So you can invoke them as an oracle. You can get the responses, but you really do not know what's happening underneath. Or it could be that even these components are stochastic. So you are not even you cannot even hope to get some sort of a deterministic response, or you cannot even hope to get some sort of deterministic response. But even in such cases, you can try to get some sort of a probabilistic guarantees on the execution of their program. So let me just make one thing very clear. I am not interested in understanding what foo does. We are more interested in understanding what does our program do in the context of this function foo. Right? So, like, just to make things clear, like, for example, if I'm calling foo under certain guards, right? And this guard could be, let's say, A is greater than 0 and B is greater than 0. I really do not care what happens in foo when A and B are less than 0. So I only care what happens to foo in the context of what our procedure can or our program can invoke foo with. So it makes the problem slightly more easier than certain approaches where they try to understand this function foo in its entirety. So the solution that we propose is a combination of proof-based techniques and testing techniques. So the question is that, can we build like effective engines using testing and proof engines together? So now testing could be either fuzzing techniques or some sort of random sampling, or it could be proof techniques that you could get using SMT solving or some computer algebra libraries. So we sort of began this string of work almost 5 years back. This was the first work we looked at. So we we said that, is there a way of enabling reasoning on such programs on symbolic execution engines? Now, by default, symbolic execution engines come up with, they do package a very interesting technique called concretization, which out of the box supports such closed box components. So the idea is very simple. The idea is that when you are doing symbolic execution, you try to understand what are the set of values that are possible for the parameter of the function. Say, for example, in this case, x, foo is a function which we call is a closed box function, and it tries to understand what could be the feasible values of x. And from those feasible values, so you can get the feasible values of x by looking at the symbolic expression of x at this point in time when the control reaches here, and then you sample one value out of those feasible values. You concretely execute foo on that concrete value, and you try to figure out one concrete value of y which is surely feasible, right? Now the situation is that every other variable is in its symbolic form, but now y is a concrete variable. So in some sense, we have drawn an under approximation of y, and that is the best you could have done, because you really do not know what is happening in foo. So there is no hope of really getting a nice symbolic expression for y. And now what you do is you start executing the program with that value of y, and you try to see where symbolic execution takes you. Now, the problem with that technique is that you start losing coverage, because even if you look at the first branch, the value of y could either be greater than 150 or less than 150. And in either case, you will lose out on coverage, either on the right side of on the true side of the branch or on the false side of the branch. So we sort of asked ourselves that, is there a way of regaining some of this completeness back? And so we came up with this technique which we call deferred concretization. And the whole idea was that instead of concretizing foo here at the call site, why don't we try to defer the concretization to points where we figure out that we are starting to lose coverage, and we try to find out values which can sort of grow the symbolic execution even on those directions. So, for example, in this case, we could have lost coverage on this branch, and our technique can sort of produce a feasible node in the symbolic execution tree at that node, and it can continue. And it sort of makes us reason on certain quantities which are slightly complex. So essentially, the way we do it is that we sort of maintain both an over approximation and under approximation of the symbolic expressions in the program. And whenever our under approximation works, it's well and good. But when they don't, we try to use the over approximation to try to find some sort of feasible expressions, some sort of feasible values that can regain the lost symbolic nodes that you might have lost concretization. So, and the way we solve it is that we first take this symbolic formula that we get. We try to use a logic solver, an SMT solver, to solve it first. We in fact solve an under approximation of this formula, which means that whenever the formula is unsatisfiable, you know that you could not produce a satisfiable assignment, but it is possible that the formula still has certain other satisfiable assignment. I'll sort of go into these things in more detail, but in a different application. And then you can essentially use a fuzz solver that we sort of invented to say that, can we still find out a feasible assignment? And the guarantee we could give is that in case our solvers were sound and complete, our technique turns out to be sound and complete. So
Subhajit, I have a question. Madhukar here.
Yes.
Yeah. So you're trying to find the values of y which can cover all these branches in some sense.
Yes.
And you said that you're going to employ a solver to do this to help you in this task.
Yeah.
But you don't know the constraints that foo poses, really, right? So
exactly.
So how?
So basically, what we do is that, I'm in a very high level setting. So what we do is we filter out all the constraints which Pau has. So okay, so let me just go a little bit deeper. So if you look at each of these closed box call, here there are many. For example, there is ceiling, there is power, there are many of these functions. And for each of these functions, we maintain, for example, if you look at it, we maintain alpha2, which is a symbolic component. And we also maintain 0, which is a concrete component. So the concrete component gives you witness of a feasible assignment to this particular function. And what we do is the first setting, what we do is we do an under approximation of this formula. So we pull out all the concrete settings, the concrete values, and we know that if we get a satisfiable assignment with those concrete values, my satisfiable assignment of the formula will indeed have a feasible execution of the program. So if we get a satisfiable assignment, well and good. If we don't, it doesn't mean that the original formula was unsatisfiable. So in this case, what we do is we take this formula and we devise a solver, which is based on program fuzzing, which we run on this. And because it's a testing technique, it can run through foo. Okay. So we execute foo in that setting, and we try to find out feasible solutions which can work overall.
Okay.
So yeah, so it's a combination of, so again, because fuzzing is not complete, which means that you could lose out on possible satisfiable assignments. But the guarantee is that whenever you get a satisfiable assignment, it is guaranteed to be sound. Like it is guaranteed to be indeed a correct satisfiable. Okay. Yeah. Thanks for the question. And this technique works well because it like over CLI, which is from the state-of-the-art symbolic execution engine, with the concretization setting, the default setting, it gets more than 67% branch coverage. And if you try to say that let's try to make everything symbolic, it really gets more. But let's not get too much into it. But and the other interesting thing is we tried to find out how much of the symbolic execution tree we are missing out. And we found out almost 40% of the tree that we could construct, CLI was completely missing out. It could not even get into those parts of the tree or those subtrees. So after this work, we started looking at, can we do the same thing with other program analysis techniques? And we picked up, could we do program inductive verification, for example? So here we said that we took the question of finding invariants, but then because we were using program testing techniques, we call them almost correct invariants. So this was led by my student Sumit. And so the idea was that can we take the proof of a program and compile this proof? So here we have a specification and a proposed invariant I. Using them, can I construct a non-deterministic program somehow such that we can write a theorem that if certain locations in this particular program are unreachable, then the invariant must be a correct invariant and must be the case that we have been able to find a proof of correctness for this program. So for the rhetorical, we again use fuzzing, and we say, can we use a fuzzer to search through this non-deterministic program for a correct invariant? However, we do something else. We found that there are certain parts of the program we can still use an SMT solver, which is faster and more efficient. But wherever we cannot use an SMT solver, we try to use fuzzing. So we call it proof fuzzing because it is not really fuzzing the original program, but it's fuzzing the proof of correctness of that program. So then we again took this work, and Pankaj led this work on synthesizing abstract transformers. And we said that like if you have an abstract interpretation engine, can we automatically come up with abstract transformers for it, given concrete implementations of these closed box functions? And so we were able to synthesize many such abstract transformers across multiple domains, string domains, bounded interval domains, and so on. And again, we use a synergy between a theorem prover and a fuzzer in our endeavor. But today's talk is going to be again in one of the work that was led by Subhajit, and it appeared in USPA last year. And this work was about, like, now having experience of this work, can we sort of isolate our technique into a more versatile tool, into an SMT solver, such that the SMT solver can reason in context of such closed box implementations. So we call it like a conflict driven fuzz loop, sort of a take on the CDCL algorithm. And we say that we introduce this theory of closed box functions, and we say how we can change the how we can modify the SMT routine, the SMT implementation to start reasoning even in context of implementations for which we do not have the logical formula or the source code available. So let me just set up the context of what we are trying to achieve here. So the idea is that we have a formula in some fragment of first order logic, and in this fragment we also have such formulae, in this case bar, the function bar, which looks like an uninterpreted function, but we have provided an executable interpretation of it in the form of a library that I could have provided along with the function, or maybe an access to an interface which could call a web API or something like that. So we have some sort of a executable interface to bar. Now it could be an external library, it could be a web API call, whatever form, but it gives me a way of executing bar. So we call these functions closed box functions, and so these functions should satisfy certain conditions. One is that they must be functional. So every time I call them, they must return the same value. And there must be a proper input-output interface available for these functions. So I must know how to call these methods, and I must be able to call these methods, right? And now what we want to do is that we want to solve formulae across these formulae of these forms which have such functions. Like for example, I may want to solve something like u equals 6 and bar of uv is 42. And if you just run it with a standard SMT solver, it would just treat bar as an uninterpreted function. It may give you a satisfiable assignment which looks like u is 6 and v is 0. But if we have an implementation of bar available with us, we could see that this will not be a satisfiable assignment in the context of an implementation of bar which just multiplies u and v. So now what we want to do is we want to sort of zero on one of those assignments of u and v, which of course satisfies the formula, but at the same time is consistent with this implementation of bar which is available with us. So in all the previous work that we had seen so far, the idea was to reduce satisfiability of a logical formula to the problem of reachability in a program. And I think this itself is a very interesting idea, because the verification community throughout has been looking at the other direction. They had been trying to take a program correctness problem and compile it down to a satisfiability query. And here we are doing the other way around. We are taking a satisfiability query and saying that, can we translate it down to a reachability question on a program? And then once we do that, the whole reason for doing that is that to enable the use of these magic fuzzers that have been around for some time now, to also help us do program reasoning. So we compile these down to reachability queries on programs and use fuzzers as a reachability oracle to answer these reachability queries. So that is the core idea of how you could go about this task. So now if you start looking at how the work that I was talking in the previous slides, how do they tackle this problem? If you look at Colossus, the symbolic execution engine, I'm sorry. So it basically sort of does some sort of a semantic division of the program. So it sort of takes the program, tries to get an under approximation of the formula. If the under approximation turns out to be SAT, all good. If not, then it tries to compile the program into a C program and use a fuzzer. Achar, which was the invariant generation engine, what Achar does is it sort of takes a disjunctive partitioning of the program. It tries to find out program paths on which we could do symbolic reasoning. So it just partitions the program into those set of paths where program reasoning with pure SMT is possible, discharges that to a SMT solver. And the other disjunct, it only keeps the parts of the program where you really need a fuzzer to work. And that disjunct it actually gives to a fuzzer. And if both the partitions like tell you things are unsat, then it is unsat. If any of them give you a satisfiable solution, you are happy. However, the problem with these techniques are there is not much interaction between, so the fuzzer and the symbolic execution, the fuzzer and the SMT engines are sort of working in isolation. So they are not really talking to each other. And the whole, so the idea that we had by then was that, is there a way of sort of make the solving more interactive between the SMT solver and the fuzzer? And that is where we came up with this, the tool Sadak. So as we said, so we introduced the CB theory, which is the theory of closed box functions, to support closed box function within SMT. And we invented this algorithm called CDFL, a conflict-driven fuzz loop, for solving constraints over solving CB constraints. So this is how the interface looks like. So when you want to invoke Sadak, you have to give it a logical formula in the form of it accepts thing in the SMT-lib format. And you also have to give us an implementation of the closed box functions. So whatever you have specified as closed box in the SMT-lib file, you also provide us the implementations for them. It doesn't have to be the source code. You could just, even if you give us access to a web API, that works for us. So this gray box means that I really don't care what the implementation is here. And Sadak will give you a satisfiable solution, which is consistent with the SMT. Sorry. Yeah, so this, right. So Sadak will give you an SMT, will give you a satisfiable solution, which is consistent with the SMT formula, as well as is consistent with the implementations provided. And Sadak is sound but not complete, which means that any solution it provides is indeed a valid solution to the formula, but then it may not be able to produce a solution even if one exists. So this is what the SMT encoding looks like for Sadak. So it's a standard SMT-lib file, but we extend it by this additional declaration. So you can also say declare CB for declaring a closed box function. And the rest of it is very similar to how you provide the definition for UFs, for uninterpreted functions. And of course, we also demand implementation of whatever is specified as a CB function. So whatever has been defined as a CB function here, we demand the implementations of or executable implementations of those functions.
So Subhajit, why do you call it closed box and not black box?
Okay, so that's a more so nowadays black is supposed to be not a nice word to use.
Okay.
Okay, so yeah.
Okay, so okay.
So nothing technical as such. So
Nothing technical. Okay.
So that's why we made it gray, not black. Yeah, I mean, yeah, these are like black box functions. Okay, so now this is the signature of our theory. So you have the regular set of sorts that you could have in a regular SMT format. You could have a set of sorted constants, function symbols, but we also extended by these the sorted function symbols for these closed box functions that you could now also provide. Predicates from the theories, and we need what we call the rewrite schema. So this rewrite schema is a way of sort of exchanging information between the fuzzer and the the fuzzer and the SMT engine. So basically, this is a way of saying how does something in logic really execute within a fuzzer. So it sort of gives you a way of saying, and this is user defined. The user can specify what does an int really mean when you're executing it. What does an expression add of two numbers mean when you're executing it? So the user will have to give you these sorts and these expressions. So we, in Sadak, it already packages the rewrites for bit vectors, but you could add your own theory to it the way you want. one thing to note, we can sort of work even without the rewrite functions, but then it doesn't work as effectively, because if you give good rewrite functions, it can exchange a more richer set of lemmas between the fuzzer and the SMT engine. Now, so now let's say this is the function, this is the logical formula that I'm interested in solving. And so the first step, as is in any SMT solving, is purification. So we try to purify the formula into different theories. And this is what the purification step is. Essentially what we have done, we have pulled out the CB terms separate from the other terms. And now we segregate the formula, we separate out the formula, and the SMT engine is given access to all the SMT terms, all the theories that the SMT solver understands. And the fuzz engine is given all the fuzz terms that the SMT solver does not understand. So this is sort of inspired by the Nelson Open procedure, if you're aware of it, and you'll see a lot of similarities down the line. But yeah, so now let me just walk you through how this whole thing gets solved. So to begin with, we run.
So sorry, Subhajit, what was the original formula?
So at the top,
So f is the unknown function, is it?
F is the unknown, is a CB function. So here we had like both f of xy and like a comparison with 255. So we separate out it into two different theories separately. So we pull out z equals f of xy and then say z is greater than 255. So I can give it for integer reasoning and I can give it for CB reasoning.
And the goal is just to give say whether it is there is a satisfying assignment.
So is there a satisfying assignment to this formula? And that satisfying assignment is a valid execution of f of x. Right,
but I mean, you want to give you don't want to say sat or unsat.
We want to say sat or unsat along with the satisfiable assignment.
I see. So how will you say, okay, you could still say unsat, for example, by treating f as an uninterpreted function.
Yes, exactly. So even by treating f as an uninterpreted function, if the whole thing comes out to be unsat, then we know it is unsat.
Or you might, like in that bar example you had, you know, if bar on 6 doesn't give you, 42, then also you can say unsat, right? I mean, let's say bar had only one argument, u.
Yeah, but if your domain of this function is restrictive, then you can still, because you can run through all assignments and you can still say unsat. But if your domain is infinite, then yeah, you may not be able to see that.
No, not the, I mean, because you're only calling bar with, let's say, u equal to 6, you know.
I see. Yes. Correct. But that will even get with an uninterpreted because now we can start taking multiple values.
Uninterpreted won't say unsat, right?
Here it will not, because it can keep on giving you values for v, which are.
No, let's say v was not there. Let's say I just had bar of u equal to 42.
Yes. You can just run it and you'll learn a lemma which says bar of 6 is not 42. And then you can say it is unsat. You're right. Correct. That's true.
But uninterpreted function wouldn't say that. I mean,
uninterpreted function will not say that. Yes.
Okay.
Yeah. So we learn such lemmas and together they can, yeah. So we basically learn an uninterpreted lemma in such a case, which says that bar of 6 is 42 or not 42. And then the SMT solver can say even with uninterpreted function, this works because it has learned that lemma.
Right.
So so let's start with this. So to begin with, we take this fuzz engine and we try to run the fuzzer on our this cute f of CB, and we try to get a partial model. So basically, we get one execution out of this program, and we get some assignments of to x, y, and z. Now we take this partial model and we propagate it to SMT. So now we see that we get a conflict because it says the SMT engine must ensure that x is greater than y, but in this case, of course, x is not greater than y. So we get a conflict. And this makes us realize that this particular term was perhaps important for CB reasoning as well. So now what we do is we pull this construct back into the fuzz engine, and we say, can you give me a different assignment, a different partial assignment, knowing that X must be greater than Y. So the fuzz engine now again refines its model. And okay, at the same time, like I was saying, so the SMT engine also learns this fact that, so the SMT engine takes this F as an uninterpreted function, and it learns the fact that even on that uninterpreted function, I know that with 0 values, this is supposed to give you back a 0. So in some sense, what has happened here is that we have enhanced both the engines with some added knowledge from each other, right? So the SMT engine starts knowing a little bit more about what was happening with the CB part, and the fuzz engine gets to know more about what is happening with the logical theory. So then in the next iteration, we again tries to define the model, and we get a different partial model. In this case, X equals 1 and say Y is equals 0, because it now knows that X must be greater than Y. And this is propagated back to the SMT engine. Now the SMT engine again gets a conflict, and it figures out that Z has to be greater than 255. So again, we know that Z is greater than 255 was perhaps important for the CB engine, and that is pulled into the CB engine. And at the same time, we learn a new lemma for the SFT engine, saying that with f of 1, 0, you must get a 0. Right? So the same thing happens further. So we get another partial model. X is something, Y is 1, Z is something. And this again, we propagate back to the SMT engine. And we again get a conflict. It knows that Z must be less than this particular value. We learn a new lemma back from the SMT engine, and a new lemma back for the SMT engine, a new lemma from the SMT engine, a new lemma for the SMT engine. So it again learns that with 6, 6, 5, 5, 3, 6, and 1, you must get back the same number back. And the same thing continues. Now you get another partial model from the fuzzer. We propagate it back. And now both of the engines are consistent, so none of them get any contradictions. In fact, the SMT engine rather doesn't get a contradiction. And then because everything is consistent, we can extend this partial model, append it with the model from the SMT engine, and produce a full model. Sorry, what happened? I'm sorry, really sorry.
Subhajit, so why do we have to do it one constraint to the first engine? Like if you look at the function, all the arguments will eventually be required, right? All the constraints from the arguments.
You don't know. I mean, so we don't even do that sort of an analysis. We just say these conflicts will tell us what is required, what is not required. So we will get this semantic. So there can be a lot of syntactic constraints which may not be relevant. So why overburden them? We don't know. So
also here, I think it was all conjunctions, right? So
yes.
That's why Alvin is saying that you could have taken them all, but you might have like a general clause from disjunctions of conjunctions, conjunctions of disjunctions.
Okay.
Something is stuck. Okay, so now we have taken the solution from the fuzz engine and extended it with the solution from the SMT engine, and we combine them to get a full solution. And this solution, you can see, is consistent not only with respect to the formula that we are required to solve, but also with respect to the closed box function. It also respects the semantics of this function. So at a very high level, this is how the translation works. So the idea is that you have an SMT formula, And we have a translation schema that is provided by the user. So this translation schema, so we already provide something for bit vectors. So this translation, along with the translation schema, and the translation schema helps the translation of this SMT formula into a file, into a program, into a C program, which is quite simple to see why it works. And we use a fuzzer on this program to find out feasible assemblies. So that is what is happening for the fuzzing part of it. So just to summarize, this is exactly what's going on. So we have the constraints in the SMT format. We first do segregation. It does two things. One is it does purification, and then it separates out the terms into terms for the fuzz engine and terms for the SMT engine. The fuzz engine sort of does a partial, creates partial models which are fed to the SMT engine. The SMT engine searches for completions. If it's able to find a completion, we are done. If not, it gives a conflict, which case both the fuzz engine and SMT engine exchange relevant lemmas. So there is some conflict analysis and they exchange relevant lemmas. And this process continues, what we call CDFL continues till we get a consistent model. Keyboard is.
Does it mean that the fuzzer is always working with a formula, with a conjunctive formula?
Not necessarily. Well, inside the, you're talking about the fuzz engine or the SMT engine?
No, when we pull in lemmas into from the SMT engine into the fuzz engine, does it mean that the fuzz engine treats that set of lemmas as a conjunction of all those?
Yeah, so generally within SMT solver, both the fuzz engine and the SMT engine eventually keep everything in as a list of constraints. So the fuzz engine also will eventually have a list of constraints to work. So you will compile the disjunctions out.
Okay.
So because at the backbone of this is a SAT solver, like for SMT solver is essentially driven by a SAT solver. And the SAT solver generally works on CNF. So eventually you will have things in CNF.
Okay.
Okay, so now in terms of the related work, so there was one engine which sort of handles closed box constraints. And this was something when we discovered when we were writing our paper. And this came very recently last year at VMKI. And what the engine does is that it follows a different methodology. So it actually doesn't use a fuzzer. It instead drives everything through the SMT solver. So it has the SMT constraints. And whenever it tries, the SMT solver proposes an assignment. And so there is a function available, the executable function. The executable function validates if the assignments work. So if the assignments work, all is good, and you get a satisfiable assignment. If not, you learn new UF constraints, which tells you behavior of the function, the closed box function, and those are added back to the SMT solver. So in this case, you can see that learning is only one-sided. The SMT solver incrementally starts learning more and more and more and more about the function, the closed box function. So we compared our approach with this approach. And so we built our tool with two modes. One was the CDFL mode. At the same time, we also had a fuzz mode. We said that why not take the whole program, compile the whole thing into a large program, and then fuzz the whole thing. So we take a formula, compile it down to a C program, and just use a fuzzer to find satisfiable assignments. So that is the fuzz mode of something. So as you can see, so the Delphi tool also works in two different modes. One is the bit blasting mode, where it just bit blast everything to SAT and then solves it. The other is the SMT mode. So as you can see, even
so how do you convert the whole thing to a fuzz?
Yeah, so basically, because at the end of the day, the SMT solver would have created a CNF for us. So it's just a conjunction.
Okay, so then you
just have an if ladder, which just checks each of them.
Okay, so you'll have multiple instances for the fuzzer.
Yes. No. I mean, the same program. It's very similar to this. Let me just go back. Sorry, what am I doing? Right. So it's sort of like this. So you have an if ladder which says the first term must be true, the second term must be true, the third term must be true, the fourth term must be true. If all of them are true, I try to crash my program. And so whenever my program crashes, I know that I've got a satisfied assignment.
But if you have like a disjunction now,
you can also have a disjunction in the, so you can say z is equal to f of xy or something.
Okay. But essentially each conjunct would be like a path in the
yes, exactly.
program.
So so even the fuzz mode of Sadhak is able to beat the best mode of Delphi, the bit blast mode of Delphi, and the CDFL mode, of course, does much better. So we are able to solve 101 of our benchmarks where Delphi, the best mode of Delphi, was solving around 62. So, so to conclude, we introduced this notion of the closed box function theory and proposed this algorithm called CDFL to solve over it. So Sadhak is built on top of the CBC4 solver. And we've also proposed the set of benchmarks which contain these closed box entities you can reason on. And the paper and the artifacts are available at this site. And thanks to Sujit for making these wonderful slides and letting me steal them. So yeah, so I will be happy to take questions. But given that I was given the stage, I was really tempted to put in a really shameless plug. Let me quickly go through a couple of more slides. So recently, so I have been teaching program analysis for a long time, and I have been really troubled by how to really teach this course effectively. And the biggest problem I face is giving assignments to students on the set of topics. So again, I think all of us teach this course in different ways, but our course is a more breadth course where we teach a lot of topics, but not too much in depth. So to teach this course, we have recently built a framework called Chiron. We just recently presented it in AC. So it gives you a very fun source language to work with. So we have this language called Turtle, which is used to teach programming to kids. And we said maybe it can be used to teach program analysis to kids. So we take this very fun source language. So it allows you to draw things on the screen and so on. It has a very simple IR, a very, very small code base, and very plug and play extensible architecture that, I mean, I would even welcome if you guys are interested in adding something more to this. And if you look at the code base, it's a very, very small code base. And so this is the third offering of of our program analysis course that we are running at IIT Kanpur with this tool. And we have been pretty happy with how the students have responded to it. So the assignments are also very fun assignments. So for example, let's say we want to give an abstract interpretation assignment to students. So the way we do it is that we give it a program and we say the program is some sort of a map for the turtles to move around. And there is some part of the canvas which is sort of controlled by alligators. And the question we are asking is there a way for the turtle following this map, which is a program, to somehow go inside the alligator's territory, right? So essentially, we are asking a reachability query saying that, is there a way that the program state can enter an error state, which is the alligator state? So, but we present it in a more fun way. So we have some fun assignments for data flow analysis, control flow analysis, abstract interpretation, fuzzing, statistical bug localization. I don't know, I'm missing some, but yeah, I mean, abstract interpretation. So we have created such fun assignments on Chiron, and the source code and the paper is also available. So which also talks about the assignments and how everything is set up and how the students responded to this whole thing. So in case you are interested in using Keron in your courses, we'll be very happy to support them. So please let me know, and we'll be very excited in case you think that it can be something useful for your course. So with that, I'll sort of end my talk, and I'll be very happy to take questions.
So yeah, thanks, Subhajit. Great, very interesting work, great talk also. So did you look at any downstream applications? I mean, I'm assuming that this symbolic execution problem initially spoke about would benefit from such a solver.
Yeah, so there are pros and cons. Like, I think that the symbolic execution engine had a very tight integration with the fuzzer, and that sort of helped because it was the whole algorithm was driven to just do symbolic execution. So I think that's still a very effective algorithm. But with Sadhak, I think we have a lot of, it gives you a very general purpose solver to plug it into any application that you are interested in. And we are looking at some of these applications at the moment. We have even, like, we are in the process of sort of seeing if we can do something with like these proof solvers like F-star, which also use E3. So can be integrated within them. So we are also looking at, like, we have also tried to put it in within Euclid. That's a tool that Sanjeet has, still something going on there. And there are certain more applications we are still looking at. So yeah, we are sort of trying out something. At the same time, we are also looking at more work, because we don't think that we are still there with Sadhak. I think there are still a lot of places. One of the places is fuzzing. I think we can still improve the fuzzing for Sadhak for such applications. So there's some work going on at the moment along those directions as well.
So nothing on verifying programs.
Verifying programs, yes. I mean, so the deductive verification framework with Achar sort of does that. So that also sort of worked out very well. But again, we have not really put it in a verifier as of now. So Euclid does that, because Euclid gives you a high-level interface for verification, and it uses an SMT solver underneath. So it was sort of easy for us, because you do not have to really worry about like constructing constraints and all these things, or working with, so we just get the SMT formula in its pure form, and Sadhak can solve it. So that is where we are still trying to integrate it with some sort of a verification.
Okay. Are there any other questions? Okay, maybe there are no more questions. Madhukar, would you should we wind up, or do you have any? Madhukar is there.
Yeah. Hi, Deepak.
Oh, okay.
Yeah, so I think, if there are no further questions, we can wind up. Of course, I'll make the recording available, and should there be other questions, then people can write to Subhajit directly. Yeah. So Subhajit, once again, thanks a lot for.
No, I mean, I think our pleasure is all mine, and thank you for the opportunity. Madhukar, Deepak, thank you so much for the opportunity.
Okay. Yeah. Okay.
Thanks, Subhajit.
Thank you so much.
Stop the recording, and then we can.
Sure.